It's amazing how much science has advanced, both the combination of AI and the ability of advanced biosensing. But now you can start asking the question, can I start understand diseases and maybe can screen for Parkinson's, Alzheimer's? Our algorithm capture these changes and then the AI interpret them after learning. And it worked.
We're at MIT, inside the lab of Professor Dina Katabi. Her team is developing systems that can track human motion without wearables, using AI to recognize subtle patterns in how people move, breathe, and sleep. The technology can help detect early signs of disease, including conditions like Parkinson's, often before symptoms are obvious.
So the wireless device is this one. Like this is a wireless device, just
that's a device.
Yeah, and so what we are going to show you is like how the device get the person. It analyzes the reflected signal from the moving object and it starts creating the key points like head, shoulders, ankles, and all of that stuff. So the AI understands when he's moving, it's tracking the moving object in particular. It knows that humans are the reason of motion in the environment, and the static objects are probably furniture. The signal reflects off his body, so he's raising his hand. You see it detects it.
Wow.
By the screen. Can you imitate someone who's older, maybe a hunched? So because it's tracking key points, so it knows now that the shoulders are lower than the rest of the body. So so it can track that and show, for example, if somebody is having different move, pain or something like that. Millie, maybe you can go in. So if you want, you can try sitting on the couch and let's see whether it will detect that you sat. So so it detected you sitting on the couch.
So imagine if I'm a grandpa, stay home by myself, and I suddenly fall.
Yeah.
And then if in the future these devices can sound alarm,
exactly.
that'll be very helpful.
Yes.
To understand how reliable this system really is, Dina walks us through the data. She compares her wireless scans with traditional tools like EEGs, showing how closely the results align.
So this is, for example, EEG signals. And this is the EEG measured from the electrodes. And this is the EEG that was generated from our AI.
Whoa.
Yeah, and as you can see, all of the
This
structures.
one is generated.
Yeah, completely generated. We tried this same method on over 20,000 different individuals, and the error is very small. What we call in AI mean absolute error is 7%. That we are using this model to try to do Parkinson detection, Alzheimer detection, and antidepressant use, and they all this metric is what we call AUC or AU-ROC. So you can interpret it as accuracy. It's really interesting. I mean, it's some of the stuff that is possible 6 years ago, we would not have imagined the kind of technological advancement that we see today. If you asked me, as I said before, that we would be able to generate EEG from someone respiration, even directly from the wireless signal, I would say this is impossible, but it is possible.
What make you starting this subject? It's quite unique.
It's really interesting because if you talk to me 10 years ago and you would tell me that with just wireless signal we can get someone's breathing and even EEG, I would tell you are dreaming. But it's amazing how much science has advanced, both the combination of AI and the ability of doing really advanced biosensing. So when we started, we were just curious. I mean, basically, that's I think how most scientists start. They just I worked a lot on wireless systems, so I know the characteristic of wireless signals. And at that time, AI was like we were starting to see like the advances of deep learning and all of that stuff. So we were just curious about like whether we can track people, and we started with movement. It's like basically, can we see people through walls, like because wireless signal traverse walls, and we were like, okay, so maybe we can like get X-ray vision or something like that. But then around that time, both me and my student, my grandfather and his grandmother had health issues, and they fell. And we live, of course, his grandmother, I think, was at the time in Lebanon, and mine was in Belgium. So we were both like, oh my God, if I can use this to just track the health metrics of the people I love, and that I could never convince them to like wear wearables or do like stuff on their own, that would be helpful. So that's where we got on it.
When you develop this technology, what are the first breakthroughs that you see that it could be possible?
So as I said, we started with the motion. The motion was something that is more straightforward. Like we know, for example, radar system. So radar system is like you can detect an airplane in the sky. So what we thought is that maybe we can use something similar but on consumer kind of radar, so that we can track people motion. And as we said, like particularly for elderly, we both, like me and the student at the time, we had elderly grandparents that we wanted to be able to detect falls for them, for example, or balance issues that we were very much worried about them because they live alone. So we started with motion, and of course taking a concept like radar, where it's just like you're tracking an airplane in an empty sky, is very different from like consumer device, very, very low power. You can't use the same power as radar, of course, and smaller device, much cheaper. And at the same time, everything indoors reflects. It's not like an empty sky. So we needed to develop a new technology for that. But we started with motion, and then we moved to vitals, and then we just, maybe like even things that have nothing to do with motion, like sleep staging, knowing whether someone is in light, deep sleep, etc. And it continued. Then we started working with patients, like the Parkinson's study that we were just talking about earlier.
Could you bring us into the science of it?
The science is, there are multiple aspects to the science. So the first aspect is how can you like track someone's motion, as we said, like with wireless signal, even through walls and occlusions. And the reason for that is simple. It's just like if you have wireless signal or electromagnetic waves, they bounce off the human body. So if you have the ability to have if you put an antenna and you start attracting or collecting these wireless signals, then it's kind of like you have an ear that hears wireless signals. Okay? Now you need the brain. And this is where machine learning comes. So the brain interprets those like minute signal that the antenna captures. And now with AI, you can interpret things that we couldn't interpret in the old days. Like, okay, so this is actually the pulsing of the blood. This is the respiratory signal. This is a person who's walking, like this is the right foot, the left foot. They sat now. So you start having ability to interpret more with AI, as I said. It's like the ear and the brain. The wireless is the ear, the antenna, and then the brain is the AI.
Could you dive deep into the Parkinson's disease detection?
Sure. So as I said, there are multiple scientific breakthroughs that go into this. So the first thing is what we talked about, which is capturing vital signs and motion. But now you can start asking the question, can I now, if I have the ability to capture people physiological signals all the time, can I start understand diseases and maybe can screen for Parkinson's, Alzheimer's, and all of that stuff. And this is where AI actually again comes and plays a very important role. It's a set of patterns. So it's a sequence of patterns, and there are rules, and like these patterns come after each other, not randomly, but according to certain rules that we don't know. And so if you take your EEG, for example, your brain EEG or respiratory signal, the patterns, you could think of them as words in the dictionary. So now you can, as opposed to English, for example, where we know the dictionary, we know there is a dictionary, but we don't know the words in that dictionary, but we can learn them from data. So the first step is like we start learning those words and like what are the patterns that appear in the signal. And then we learn how to interpret them.
Okay.
So in the case of Parkinson, in fact, what we discovered is it's very interesting because I have multiple things about Parkinson. So one of the things when we started working on Parkinson, I was working with amazing colleagues, Ray Dorsey and Alex Vidanovich, and I was asking Ray, like, can we detect that somebody has Parkinson without the motor symptoms? In fact, I asked him first question, like, why do people stop like tremoring when they are asleep, for example? And there's so much that is unknown, but he is like, okay, so like he told me that most of the time we detect these diseases much later. Right. Because we are waiting for the motor symptoms to appear. This is when we typically know that the person may be like they have Parkinson. But actually autonomic changes happen much earlier, like changes in sleep and changes in respiratory signal. In fact, even James Parkinson himself, he wrote about changes in the respiratory signal in the early patients he looked at. And because Parkinson also starts in the stem of the brain, so the control of the breathing exists in those areas. So there is strong connection. So I thought, okay, maybe we can like just try AI. Maybe you can detect Parkinson from someone's breathing.
Like smaller signal before the tremor, right?
Yeah. So if we can detect it from like the respiratory signal during sleep, then hopefully we can detect stuff before even the person starts developing motor symptoms. And I guess, again, curiosity and trying, it worked. And we were really surprised at the beginning, and we kept trying more and more, and just like, yeah, it does work. And in fact, of course, we can't tell. We can tell, we did a study with a very large number of people, like it has 7,000 individuals, 700 of them have Parkinson's disease, and we can show that we can detect the one who have Parkinson's disease with very high accuracy. But the other question is, can we detect it before it's diagnosed by a doctor? And we don't have, like, of course, that's much harder to ask that question because you need to have a person and to know that this person eventually is going to have Parkinson.
Yeah, you need to track.
Yeah. So that takes sometimes like 10 years plus. So we found a data set where we actually can apply the machine learning to the breathing of people. And early, like there are two visits. They came, two visits that are separated by 6 years. And we can look at the first visit and see what the algorithm is going to say about people, like who has Parkinson and who doesn't. And then look at the data from the 6 years later, who came and said, oh, I got diagnosed with Parkinson. And interestingly, actually, for 75% of the people who eventually got diagnosed with Parkinson, the algorithm knows, like saying, oh, no, I think these people have something. They don't look like the normal people. They look more like the Parkinson people. Of course, this study is a smaller size, so we want to like now get more data because we need to show like, okay, so under what condition, how much earlier, all of that stuff. Because Parkinson is also a very complex disease. It's not really one disease. It's a combination of things that we call Parkinson's.
Is there anything they can do to prevent it at this stage?
Unfortunately, with much of the neurodegenerative diseases, we don't really have very effective cures to the disease. We do have like things, like in the case of Parkinson's in particular, I mean, Alzheimer's is slightly better recently, we got something. But there is nothing that cures the disease. But knowing that the person has certain symptoms, or has something that is building up toward the disease, can be very helpful in explaining and starting them on certain drugs to address some of the side effects. Like I was talking about this in a conference, and actually a patient came to the mic and said, although there is no cure, like it's not like if you tell me that I have Parkinson, the disease started with the patient was having like breathing and epilepsy problems, and the doctors would give him things that have nothing, drugs that have nothing to do with his disease. But it turned out that he has Parkinson, and eventually, once he got diagnosed, they actually can treat him properly.
And I would like to understand from all the data you collecting, is that come from your lab or is come from a wider database?
So I work with medical doctors both in hospital systems, and like I mentioned, Ray, Alex, and my colleague that I worked with on Alzheimer, Ipsit-Vahia, for example. We are working now on depression and detecting non-adherence with antidepressant. And we can detect who's taking antidepressant without questions.
You can detect from the machine?
Yeah,
How?
Just, because when you take a drug, not just disease changes change your physiology, also drugs change the physiology. So you can tell like that someone is taking like particular disease, anti-depression, anticholinergic drugs, these drugs that interacts with the brain in a way. You can tell that someone is taking the drug. Actually, this again, we didn't know that we can tell, but increasingly now we have a new manuscript. We are preparing it for publication. We can detect who's taking antidepressant, no questions asked, and we actually is also sensitive to the dose. So if the person is taking higher dose, it can detect it with like give you a different score, and it doesn't get confused, for example, with antipsychotic drugs.
Is that score determined by a certain like behavioral? Like, can you give us some example? Like,
take antidepressant as an example. So antidepressant drugs, many of them are serotonergic. So SSRI, SNRI, SARI. So serotonin make changes in the EEG signal. And also the respiratory signal changes as a result. So our algorithm is capture these changes, and then the AI interpret them after learning. So we trained an AI system. We said, okay, so here's a large number of people and who don't take antidepressant, and here's a large number of people who take antidepressant. You look at the signal from these and the signal from these and figure out what's the difference on your own.
And how can a wireless machine being able to tell someone's brain waves in? I don't understand it.
I'm glad you asked this question, because most people confuse it with, again, reading the EEG, like the electric signal. If I put an electrode on the skull, in fact, yeah, it's a very weak signal. So, and with hair and stuff like this, there's a lot of noise. So we don't do that. We are taking the whole wireless signal that bounce off everything. But what people don't realize is that there is a huge crosstalk in the body between different organs and different physiological signals. And we haven't published it yet. Like we are, again, these are like new things that we are preparing manuscript for. We show that from the respiratory signal, actually, we can reconstruct with Gen AI your EEG. We are not measuring it, we are reconstructing it. But it is very accurate, much more accurate than you would think originally, because of all of this crosstalk that we as humans we cannot see that crosstalk in the signal. But like you can think of the human as like there are, particularly when it comes to chronic diseases, that there are what we call latent variables. Like there are certain things that are inside our body that say what kind of chronic diseases we have. And then they manifest themselves in different physiological manifestation, like in my EEG, my respiratory signal, my ECG, all of that stuff. But there are these connections that if we leverage the power of AI much better, hopefully over time, then we can learn way more about these connections and the crosstalk between different body organs and physiological signals.
At this moment, both of our body are creating a lot of signals, and with that antenna that are able to collecting those, and with the help of AI, they are able to put it in the right basically algorithm and come out with the right conclusion of what's happening to that person.
Yes, except that like in my work, I focus on sleep. So sleep is a resting state for the brain. So I don't want to be bothered by the particular thought or like all of the noise that can come from other things. So when we sleep, basically the wireless signal that bounce off our body can carry so much information about our different physiological signals, like our vitals, like during sleep, for example, if you are in REM sleep, like you have the twitching of these muscles, but the rest of the body is in paralysis. So it carries all of this information, and then we have very powerful algorithms that can interpret it to get information even about the EEG and even about like all of, like a variety, not all, but we know a variety of chronic diseases. Like we have demonstrated Parkinson in an earlier paper. Now we have a new result that show results about Alzheimer's as well, new results about drugs, like as I said, about antidepressant drugs, anticholinergic drugs. So, I mean, the nice thing is that we don't really know the limits. I mean, how much information we can extract, but we know that we can extract way more information about chronic diseases than otherwise.
And apart from that, is there anything else people can find from those data?
So our focus is on chronic diseases, and also it's very important, like, to also emphasize to everyone that we are very careful about privacy issues as well, because like once you have this ability, it's really important that nobody collect data about someone against their own will, and that would protect the privacy of people. So of course, every time, like all of our experiments, studies, everything is like it's similar to a clinical study, like clinical trial. So we have to write a protocol. This is exactly what we are doing, and we go to something called IRB, like ethics approval. So you go to a body and say, this is what we're going to do, and is this ethical or not ethical? And they approve it, saying, yeah, this is ethical. And then for every person that we monitor, we get what's called informed consent. So we tell them, so this is what we are monitoring. Like, do you want to be part of this? And they have to sign that, yes, it's okay. I'm interested in like being monitored for Parkinson, for like movement disorders, etc.
And also when we think about all those wireless earphones and things like that, recently there have people talking about that it might be bad to influence your health. Do you have any thoughts on that?
So one of the things that I want to emphasize, so think about Wi-Fi. Is Wi-Fi bad or good? So, I mean, you can think about it in comparison to many of the clinical trials that we have with the drugs that we take. So it's the biggest clinical trial. I mean, in comparison to the drug clinical trial, perhaps it is the safest outcome. Like, people use it, I mean, there are no proven bad things. Right? Now people talk a lot, but really no proven negative impact. Now this is different from I take a cell phone and I sleep on it every night, because the heat is actually bad to have, like very close to your brain and your ears and stuff like this. So you have to be careful in, like, if you use these technologies in the proper way, then things are fine. But if somebody misuses them, then that's not fine.
So what will be the potential future look like for this technology?
So I would imagine a future that every house, at least every house that has a patient, should have one of these Emerald devices. So it's similar to now every house has a smoke detector. You would want, like, every house that has a patient, or even if there is no patient, like you have like kids and elderly, you would want something that monitors the health of the individual. If there is a problem, detected early, personalize the care to that individual. So I would envision that a future would be like this kind of technology will exist for all of us, helping us manage our health, telling us about a problem before it escalates, and personalizing the health for, because now, like, we use just like one size fits all, which is not great, and also moving us from what we said, sick health to like really sick care to healthcare.
Yes.
The power of the technology is that it provides us with new ability for screening for diseases, for understanding progression of the diseases, impact of drugs. Basically, it can change the way we manage health completely. Not only in it increases our understanding and improve our understanding for like medical application, but also it personalizes the health because every person is different. And today, really, if you think about how the healthcare system works, it's like what people call a sick care. It's not healthcare. It is reactive. So after the problem happens, and then we start collecting data about a person because we suspect that they have cancer or something, as opposed to detecting a problem much earlier. So if we have the ability to monitor continuously to detect problems earlier, so hopefully many of the hospitalization and the ER visit can be avoided, and many of the diseases potentially maybe can change trajectory before we reach, like we say Alzheimer and Parkinson are not curable, for example, but we don't know for sure if we can detect them much earlier with proper even potentially with exercise, nutrition, change of direction. The direction of the trajectory of the disease probably would change, will be delayed, so we don't know, but if we can detect things earlier, if we can avoid this spotty, reactive way of managing health and be also personalized, then health care can be much, much better, and hopefully also cheaper, because
Yes.
the way it's going, at least in the US, is becoming unmanageable.
Today, apart from in the lab, is this technology being used somewhere else?
Yeah, so we have a startup that I started with my students, and we work with pharmaceutical companies, and as we are talking now, these devices are being used to assess new therapies in Parkinson's, in ALS, in a variety of diseases.
And do you have any neural health or health tips for our audience?
The one thing that I advise everyone, including myself, I still have problems trying to manage my sleep, is that sleep is really important. Sleep is the time when your brain kind of clean all of the toxins. Take care of your sleep if you can.
Thank you for your time today, Dina.
Thank you, Millie.
Thank you for watching this new episode of the HumanWare Project. Please like and subscribe. Your support means the world to us.